Yes. Okay. Okay. I'll solve couple of examples because this assignment has only one set of problems, that is rotation matrix and transformation matrix, which is more or less the same. Because of that, I'll be solving one example completely, and then others I would assist you. So if you have any problem, I can discuss as long as your doubts are clear. Uh, but the answers, let me not give it to you directly, or let me not solve it to you directly, because it's redundant. Once you get hold of rotation matrices, transformation matrices becomes easy. Rahul, I'll be sharing my slides. So in that slides, I'm assuming that I'll be able to clear. I'm getting difficulties in DH algorithm. DH algorithm is for week 2, and there is one question which actually works with DH algorithm as such, and that does not require week 2 knowledge to solve it. So I'll also brief you in that also. Yeah, as I was saying, so I'll be solving one problem completely so that you can see how it's done, and then others all are easy. That's what I would also suggest. Okay, so I'm still getting admit request. So apart from Rahul, anyone else is facing such problems? So discussion this week. So how can I get old lecture? No, this is the first week, and the week 1, all the lectures that you have is what is required to be seen. So the chat. Okay, there is a question by Anand in. 1 second, let me just check if my screen recording is working. Yes, it is. For mobile coordinate, do we have to consider homogeneous? It's one. Okay, transformation matrix. Okay, Anand, we'll come to that question the moment we start solving. Although I'm not able to clearly understand from the notations that you have used, but I think one problem will solve it completely. Yeah. Okay. If it doesn't get cleared, please feel free to ask me in the meeting. All right. So, yeah, Das, do you, Abhirup, do you have anything to say? Yeah. I lost your audio, Abhirup. Hmm. Yeah. So those accesses you can address it using a dot product operation, and that will result only when you are doing. So that will have a difference only when you have a rotation along the y-axis. That is the F2 that he has mentioned in his lecture. He has mentioned. So that I will show it. Yeah. Yeah. Yes. Yes, see, that is pertaining to his methods. Although I can mention that I'm not his student, so I may not be totally clear about his methods, but how we follow. So, is my slides visible? No, not yet, right? Okay, present your entire screen. Okay, so now my slides are visible, right? One second, one second. There are still people joining in, so that's a bit of a trouble. Yeah. So this is a brief about me. You'd have already known this. You can contact me through my email ID, that is vivek@isc.ac.in. If you have any queries or I have not uploaded the links or videos, you can just directly reach to me. And give me a second. And let me make it like this so that then I can see your comments. Okay. So yes, okay, I'll start the lecture later. Yeah, my slides are changing, right? Okay, there are still people joining in. Give me a second. We'll discuss this in 5 minutes of time. Okay. Everyone. Okay. Okay. Other than Abhirupa, I'll come to your question later. Since people are joining in, so I'll keep talking. I'll keep interacting till all the people join in, and then we'll start. Right. So we have 4 more minutes, and after that we'll start. Okay. There is a fellow mate from my. You will conduct these type of sessions every week. Yes, these kind of sessions will be conducted every week. Um, 4 to 5, it will be recurring 4 to 5 in the evening. And there is also another meeting that is from 5 to 6. Uh, I'm not sure who is, but he is from IIT Kanpur, and he will be also taking a session similar to ours. And if you miss this session, you can join 5 to 6. Most probably he'll be covering the same topic, although we are not coordinating with each other. Most probably he'll be taking the same content that I'll be taking, right? Yeah. If we are given four motions, two rotation and two translation, how can we multiply this matrix to get composite homogeneous transformation? Yeah, uh, that I'll cover in the last slide. Okay. Yeah, I have MTech and BTech from IIITM Kanchipuram. I guess someone is reaching out from my MTech college. Good to know. This is Manideep. Hi, Manideep. So let's get into the lecture. Please address me as Vivek. No, sir, or any other relations. Please address me by my name. And we'll just get started now. So, to answer Manideep's question, still people are joining. That's okay. solution for this. So yes, you were talking about this one, right? So it's not Manideep's question, Abhiroop's, right? I'm sorry. Hello. Yeah, you were talking about this particular negative sign, right? You can see my cursor. Yeah. So this follows this convention. This is plus, minus, plus, minus, plus, minus, plus. So that way it goes that way. So only in the top half of the diagonal you follow that convention. Whatever sign is here, the negative of that will be here, right? So let's take this is plus, this is minus, this is plus, right? Then you will have this as minus, plus, minus. So you only need to take the top half. That is the kind of notation he has. Sorry, I am at one slide, so I'm not changing slides. Are you able to see my cursor moving? All right. Is there a way to? I'm not presenting, so I cannot make pointer, right? And it's moving, right? No. Let me reach. Okay. I'll not be able to see your messages when I'm in full screen, but let us start this one. Okay. So get a pointer option. Yes. Okay. Okay. Answering Abhirup's question. Here is the top diagonal, top half of the diagonal. Here we go by plus. Okay. Let me change my pointer to a pen. Yeah. So we'll have plus, minus, plus, and this will be sorry, minus, uh, sorry, plus, minus, uh, yeah, plus, minus, sorry, yeah, you'll have minus, plus, minus, yeah, and this will be plus. Okay, so this is what he was referring to. This is my guess what he's referring to. So here you can see this is plus, right? The other part of the sign will be the opposite sign of what it is. Right? This is what he was referring to. So again here you can see plus, minus. Yes. So this will be sine minus sine theta. This will be plus. Your minus, plus, minus. Since it's 0, it doesn't matter. This is the top. Yeah. So this is what he was referring to. So that he has given an elegant way of representing it as minus 1 to the power k. Uh, that I'm not aware of, like I've not gone through his lectures particularly. So you can see also my notations are little different from his, and so but the essence is the same. He's referring to this top level. Some noise. Yeah. So, all right, let's get started with this lecture. First, before we start into this, there is a couple of history that I found that in the week 1 we did not cover. That robotics is not a recent concept. Before robotics, we had something called automata, and it is Jack Draw's contribution that automata became famous in his century, 18th century. And here is a automata that is programmable. Today, if you say that, or at those times robot can be only made, or some mechanisms can only be made to do a specific task, that is not true. We also had programmable robots. This drawing can be changed. It can write poems, it can write letters. So that entire change was coming from this stack, and that is how programming in those days was conceived. So we have a mechanism, we have cams, we have springs, and those orchestrating them to perform a task is what used to interest watchmakers. These were the people who were highly proficient with building mechanisms. And okay, after that we progressed. We had robotics, which could robots which could be programmed using a computer, or essentially a ALU, algorithm processing unit. So when we have this capability, our robots were essentially going into regions where we couldn't go. Like one case was Chernobyl, a nuclear disaster. Nobody could go to reactor 4, although people who have watched the series, they know that they use bio robots. Yes, but this was their first thought when they had to do such a task. We cannot send man there. What we do is send a robot. And here is the current day how robotics are used. It's used in manufacturing, and this is your computer aided manufacturing. And this uses robots to a very large extent to what we are going to cover in this lecture. Not only in this lecture, in this course. And this forms the basics for us to explore research and development in robotics. And today, where robots want to reach is into places where earlier endoscope could only reach, and now we want to go into finer spaces and inside our body, or inside uh, living organisms body. So this is where regions where we did not go into, and we are trying to go now. And this is one field of development. The other is controlling any robot to a desired trajectory, or a trajectory that was earlier seemed difficult to achieve. And in this lecture, I'll be taking this every Saturday, 4 to 5. We'll be discussing problems from your assignments, and also I'll be taking few simple examples to understand how in real life a robot would function given what you're studying in this course. So yes, with that, let me directly get into my slides are changing, right? Hello. Okay, so let us get into the week 1 assignment. So there are a couple of questions on what are the components of transformation matrix. So now I'm not sure what was covered in the lecture entirely. What I'm sure about is that rotation and translation matrix is covered, but um, the perspective matrix that we usually leave aside is sometimes this comes into picture when we have a mechanism that is morphing. What I mean by morphing is that the x scale, or the x perspective, like the relativity between x, two x axis, does not remain the same. And that is when this eta 1, eta 2, eta 3 assumes non-zero value. And this we do use in robotics today, but this is essentially in pinhole camera model, where we have shapes that have changed because of the curvature of the lens, because of non-uniformity in the camera sensor, and then this perspective correction comes into picture. But apart from that, the lecture covers rotation matrices and the translation matrix, translation vector, and the scaling factor. The scaling factor is a global scaling factor. So we in transformation matrix we have one, but when we go into computer graphics, The moment you scroll inside a CAD environment, what you essentially do is play with this S. This S becomes 2, 3 depending on your scroll, and this is the entire component of transformation matrix. And let us take a couple of examples of how would this look like. I assume that most of you would have solved such questions, but nevertheless it's my duty. I have to cover these questions so that we have a continuity. If anyone has a doubt, you can stop me by any time and ask, right? So this is one such incident where both the frames are coinciding. What I mean by coinciding is that yeah what I mean by coinciding is that the two frames have the same origin. The axis is, let's take x-axis of frame A, x-axis of frame B. Like here, frame 1 and frame 2, both the x-axis coincide. I mean, there is no deviation from these two axes. Y-axis coincide, z-axis coincide. When all the three axes coincide along with the origin, so we would have something like an identity matrix, which would be 4 by 4. But to split it into components, identity matrix will have the rotation matrix will be identity 3 by 3. The translation will be 0, perspective is 0, and you have a scaling factor of 1. And similarly for pure rotation, let's take this translation vector is 0. So that is the only thing that would be changing from this. No, yeah, that is the only thing that will be become 0. Along with perspective, this will be the one more thing that will be 0, and rotation matrix will assume non-zero values depending on the rotation, sequential rotation that you have performed. And the last, okay, yeah, the last example is pure translation. How do you see a pure translation in terms of a translation vector? Okay, yeah, I'm sorry, there is a mistake here. It shouldn't be 0 3 by 3, it should be identity 3 by 3. That you have no rotation that is performed, and yeah, let me just correct it. It would be identity matrix 3 by 3 along with the translation vector. Yeah, yes. So now let us come to the questions where you have composite rotation matrices. Now let us understand that this matrix multiplication that we are performing, any sequence that we go of rotation, let it be from the changing frames, like from the ground frame we go to frame 1, and then or if we are trying to make intermediate frames in between and we are rotating about those axes, that sequence has to be preserved. And that sequence cannot you can see that the matrix multiplication does not commute. The moment this doesn't commute, if you are performing a theta 1 rotation about x and theta 2 rotation about z, that is the wait, let me pull my laser pointer, that is something below, and as compared to, sorry, yeah, yeah, okay, give me a second. Yeah, is it better now? Okay, you can stop me whenever I'm not audible. Okay, it's better now. Yeah. So you can see the matrix does not commute. So if I perform theta 1 about x-axis and then theta 2 about z-axis, it's not the same as performing theta 2 about the z-axis first and then theta 1 about the x-axis. So you can see some similarities, but you can never form a relation between them. And that is one you can form relation between them, but these are not the same. So you need to be careful while picking the convention of expressing these kind of rotation matrices. So let's move forward. So there are a couple of questions on yaw, pitch and roll, right? So there is something in the lecture that was mentioned that we are rotating about the ground frame of reference, and that according to my knowledge is incorrect. What we are actually doing is we are performing a sequence of rotation about the deformed or about the changed axis or intermediate axes after the rotation. Like here I have mentioned, you can clearly see all the intermediate axes that I have given. The moment I have a yaw pitch roll, which is x, y, z rotation in the sequence, x being rotated first, y being rotated second, z being rotated the last. So here when we have x rotation, we are rotating about the ground frame, and because of this rotation, the axes must have changed their orientation. The new intermediate frame, I can denote it as x dash, y dash, z dash, and that is rotated about y dash theta 2, and you will have axis intermediate frame something like this, and this is going a sequential rotation, and finally you get your final frame. So the frame 1 and 2 intermediate, there are two frames that undergo sequential rotation. But coming to the question that can it be possible that you can do rotation about ground frame of reference? Yes, it is possible, and it is little tricky to understand that, but let us clear this problem from your assignment, and then we'll go ahead and learn how that is done. Although I'll lead you to something, but the derivation is tricky, so you can go through it once, and probably we can derive it next week. So that way we would not be grasping too much in this lecture. So we'll only be sticking to what is being taught in lecture in week 1. So there is a question with YRP rotation. This was done in the earlier run, where you have a yaw of 180 degree pi, uh, a roll of 90 and a pitch of 45. So YRP rotation, and the position of the tip after the rotation is this much. So this is an inverse problem, that the position of the tip is given with respect to the ground after transformation. So you need to find the position with respect to tip, yeah, with respect to the tool. So here is the rotation matrix after this compound rotation. So let me just quickly, sorry, yeah, quickly take you to a MATLAB program. How many of you have MATLAB license from your institute, or you have acquired it somehow? Not pirated license. Yeah, I cannot see your screen though. Give me a second. Yeah, you all admit all. So unwanted noise. Okay. Yeah, you people do have MATLAB license. Okay. People who do not have MATLAB license, you can write on the chat, and maybe I can provide you a open source way of dealing with this problem. Let us take this opportunity actually and try to learn a new software, because robotics, yes, you can, although NPTEL will ask you to perform this manually when you are writing an exam, but it's always better to know programming languages that will help you in robotics, like Python. You can use Python very well. So okay, I think there are people who don't have license of MATLAB, so I'll be providing a Python code also, where you can stepwise see how this rotation matrix is getting compounded. uh, I don't have. Okay, all right guys, there are people who do not have MATLAB license. I'll be showing this MATLAB code. It will be similar in Python. I'll also share the Python code over a presentation. There is a folder link that I'll be sharing after this lecture. Probably from there we can come to a software where everyone is comfortable with. Okay, so I'll also be uploading how to install Python, how to work with Python. I'll also be installing, but it is let me reiterate, this is not a necessity of the course. It is only that we'll be doing it ourselves. Let us take this opportunity to learn it. So it is not a mandate from the course, right? So you're not forced or compelled to install any crack software or any software by any chance. Yeah, please share Python source code analogy with Python if available as Docker image. Okay, I'll be sharing the code, and with the code you can work it out. Okay, so I have the MATLAB file now, so I'll be making the Python file and sending it to you. So here you can see one of the problems that we had taken. Here what I'm doing is a manual way of doing a problem, although you can do it much simpler in MATLAB. What I'm trying to do is that I know Rx, Ry, Rz, these are sequential rotation, not with respect to ground frame. It is after an intermediate frame we are rotating about the transformed y-axis. So this is the correction that I want to impose from what we had in the lecture by Professor Ashokan. Yeah. So here is what we are doing, a yaw pitch, yaw roll pitch type of rotation. Okay. Roll pitch type. Yeah. Okay. So what we are doing is theta 1 is being rotated about x-axis. Then there is theta 3 about y-axis, theta 2 about z-axis, and the sequence is that we rotate about first about the yaw axis, then about the roll axis, about z-axis, it rolls, and then the pitch axis, that is y-axis, it pitches, right? So this is the sequence in which we are going, and that's why I have given T3 to Ry. So let me just put it here so that, okay, sorry, let me just put it here so that there is a sequence. Okay, give me a second, I'll just allow people who are waiting. Okay, there is the queue. How do you know people are waiting in the lobby? Enlarge the font size. Okay, that's something I work with. Display settings.